All right, so I guess we need to continue from where we stopped last time, which, so let me briefly summarize what we're trying to do. The whole purpose of the discussion was to understand some properties of solids, of materials, based on the band structure ideas that we developed before. So we classified solids in three categories, well, actually in two categories. Insulators, that is solids for which insulators are solids for which the lowest available bands are all filled, and there is a finite gap of excitation between filled states and excited states, right? So we call these solids, we call them insulators. One. Vice versa, we call the metals. So insulators are systems for which the energy gap is larger than 0. Vice versa, we call metals systems for which the gap is 0, implying that the Fermi level, the Fermi energy, crosses one of the bands, of course, right? So it's the same thing as saying that the Fermi energy crosses a band, one or more bands, of course. All right? So there are clearly, the properties of these two systems are clearly different, at least some of the properties are quite different. And we're going to analyze later on an important property that makes these two systems different, which is, as you probably already guess, transport, the way they transport current, electrical current. We started by looking at optical properties. So we decided to look at optical properties. And in order to understand optical properties, we look at the function, which is the absorption coefficient, which is essentially, we didn't go into much detail about that, but essentially it's the amount of photons that get absorbed for a particular frequency in an experiment in which you're shining light onto your sample, and you look at how much light is transmitted after the through the material. Okay, and the amount of photons that get absorbed here in the material, in our solid, in our sample, is expressed by this absorption coefficient. And we argue that if the system has a gap, that this is an insulator, the absorption coefficient must have a finite range corresponding to the gap of energies for which the absorption coefficient is 0. Oh, by the way, we argued also that absorption takes place by excitations between filled states and empty states in our system. Question? No. And that only vertical transitions are allowed by optical excitations. All right. So if the band structure looks like this, we have the first transition at this particular energy gap. Well, probably this one, which is probably the same. Sorry if the plot is not symmetric. And then you have transitions at all energies larger than the energy gap, as long as there is a filled state and an empty state which differ by that particular amount of energy. So there is a continuum of excitations, and then either it goes down to 0 or there are, depending on what is the band structure above here. But the main point is that there is a window of energies, of photon energies, for which there is no absorption. And then, after a while, absorption begins. So then we discussed what are the consequences for our say, understanding of the optical properties of having a gap where the absorption is 0. And we argue that at least for for visible absorption, it is important to understand whether the gap is above, below, or in between the visible range. Okay, so it's really a matter of deciding where the visible range, which we know is between roughly 1.5 to 3 electron volts, where it is in this plot here, in this energy plot. So it's really crucial to know where the energy gap is. So if the energy gap is below the visible, if the energy gap is above the visible spectrum, and the visible spectrum again is 1.5 electron volts, 3 electron volts roughly. It's not exactly like that, but just to give an order of magnitude. If the energy gap is above 3 electron volts, that's the visible range, then the system is transparent because there is no absorption in the visible range if the energy gap is above the visible range. If the energy gap is below the visible range, that is below 1.5 electron volts, then the visible range is all within the absorption range, of course, assuming that the absorption coefficient remains finite for large energies, and therefore visible light is completely absorbed. So you don't see through that material, essentially. So here the material is transparent. We gave you example of, say, water, ice, silica, polyethylene. These are all materials that, well, whatever looks transparent has this property. The energy gap must be larger than the visible range. There are not so many, but there are a few. If the energy gap is entirely below the visible range, then the material is clearly non-transparent or opaque or something. I mean, light doesn't go through, essentially. And there are plenty of examples around ourselves of materials that don't let light go through. And of course, there is also the possibility that the energy gap is in the visible range, and therefore you may have some strange properties, like, for example, the material looks reddish because it lets red light go through and not the high energy part of the. Yes? Well, okay, that's a good question. I'll come back to that in a second. So let's stick to insulators for the time being. Let's stick to insulators. So I would say there's another statement that looks also a bit surprising, and it is this one. Even if a system is an insulator, it doesn't need to be transparent to be an insulator. Okay? There are examples of materials that look non-transparent. Actually, they look metallic. If the look of it actually shiny, metallic shiny, but they are not metals. They're still insulators because to our eyes, they absorb all the light, but they still have a gap, which is below the visible range. An example of that, for example, of material like this is silicon. Silicon, I don't know if you've ever seen the silicon wafers that they use to prepare the chips, the silicon chips. They actually look like pieces of metal. They are shiny, shiny gray. So you would think of them as metals simply because they reflect completely visible light. But they're not metals. They are just absorbing all the visible light, but they have a gap. Silicon has a gap of 1 electron volt. So it's clearly below the visible range. So silicon absorbs all the visible light, so it behaves like a reflective material, like a metal in principle. It looks like a metal, but it's not a metal. It's not a metal because there is a finite energy gap of excitation. Okay? So this is an example of something completely opposite with respect to what you're arguing. Let me come to your question now. How does a metal behave in terms of optical properties? Okay, here we need to look at it a little bit. So here we were discussing insulators here, right? Systems with a finite gap. Suppose we now have a metal, all right? So a metal is characterized by a Fermi energy. Occupied states are here. Let's try to guess. Let's try to guess. What will be the first possible excitation for a metal? The minimum energy excitation. Can you guess? Optical one. Optical one. Optical one. It is true. I mean, you can have vanishingly small excitations with this energy, but they're not vertical. You see? If you want to excite an electron from here to here, you have to add the momentum, add the k, a little bit of k. You cannot do it vertically. So the only first vertical excitation is actually this one. Right? Like this. So, strictly speaking, a metal, there's not too much difference with respect to the optical properties of an insulator, because you can actually forget about excitations within the band that makes it a metal, because excitations within this band are not possible for optical excitations with photons. Okay? So I don't need to say anything more in principle with respect to what I already said for the insulators. Well, there will be an energy gap which corresponds to the minimum excitation to the next band, because I need to go vertical, so I can only hit the next band. And then the question, of course, is what is the difference between the Fermi energy and the energy of the next band. That will be the gap that we see optically. Okay, and I could do exactly the same, follow the same arguments and considerations I considered before. So, strictly speaking, the answer to your question is a metal, from an optical point of view, should behave like an insulator. This is indeed not completely true, however, because these kind of excitations are not totally forbidden, unfortunately. These kind of excitations are possible. They have to, they involve phenomena which are beyond this vertical selection rule that we just discussed. So it is not true that these processes are completely forbidden. They are indeed allowed. A small amount, because they come from additional phenomenology that I'm not going to describe here, but they are indeed allowed. They have to do with scattering, with presence of either impurities or electron-electron scattering or other properties or other phenomena that we are not including in a simple description of the band structure. So, say, the bottom line is that these kind of processes are allowed, so optical excitations can take place by violating this vertical selection rule. They're not too large. The intensity is not too large, but it is there. Okay, so the consequence is that in a metal, in addition to the vertical excitations that you would expect based on the, say, theory at zero, the zeroth order approximation to the theory, you also have here at low frequencies a shoulder that is due to processes taking place at low energies that is within the same band. Okay? So this is what you see in addition in a metal. In a metal you see nothing else, I mean, nothing more than what you would see in an insulator, because again, if you stick to the vertical approximation, there's nothing different qualitatively with respect to an insulator. However, these vertical transitions are now, strictly speaking, verified. There are violations to that rule, and those violations become evident in the low energy part of the spectrum with a shoulder that grows at low energies. Of course, then the question is, where is the visible spectrum here? Now, in most cases, the visible spectrum is actually somewhere here. Of course, it depends on the width of this, which in some sense also depends on the width of the band here, because the maximum energy you can excite is from here to here, right? So the maximum width of this excitation band is the width of the band in principle. Well, depending on a number of, let's say, parameters, this band typically falls in the visible range. So metals, generally speaking, behave like non-transparent materials. But not all of them, not all of them. And it depends also on the number of how many carriers you have, how many of these electrons you have available, and what is the strength of this low energy contribution to the optical spectra. Okay, so the general statement, however, is that metals do behave like non-transparent systems, not because of vertical transition wouldn't explain that. You need to invoke more sophisticated processes in order to explain the low energy part of the absorption spectrum for a metal. Okay? Right. Anything else they could say about it? No, I don't think so. Well, I mean, based on these simple considerations, how would you design a system that filters UV light? Suppose you want to well, improve your sunglasses, for example. How would you think of a system? How would you choose your material in order to have something that screens out UV light, ultraviolet light? Do you have an idea how would you do it? You want to have you want to design a new sunglasses, right? For your own safety, perhaps. You want to be hit. You want your eyes to be hit by ultraviolet light, right? Because it's dangerous. So how would you design a UV filter? Something that filters UV light, and of course, lets you see through.
So, okay, I need to have a gap.
Yep.
Which is comparable with that wavelength of UV.
Right. So where is UV, by the way? Where is ultraviolet? Do you have an idea? Where is ultraviolet in the energy spectrum? Loud. Above 3 electron volts, right? So whatever is above the visible, it's ultraviolet. So ultraviolet is from 3, 4 up to, well, depends. It depends on up to 100, let's say, 100 electron volts. I'm not sure what the most dangerous one is, but certainly the sun has a large component around 10 electron volts, for example. So what, I mean, ultraviolet light from the sun is has a large component between 3 and 10 electron volts, so in the low part of the ultraviolet spectrum. And you want to get rid of that. You want to remove it. You don't want that light to hit your eyes, for example. So how would you choose your material?
So, okay, I'll choose materials with energy cap, which is less than 3 electron volts.
But not too much less than that, right? Because otherwise you don't see yourself. Okay, so the ideal material is something where the gap is exactly 3 electron volts. If the gap is exactly 3 electron volts, you will see through, visible light will go through, but ultraviolet light will not. So you have a perfect filter for ultraviolet light. It's like setting the gap here in the right range such that photons with large enough energy are absorbed and photons in the visible range are not absorbed. So, well, whatever. I mean, there are a number of semiconductors that have this behavior.
Related to polarization, I mean, sometimes we can select the one.
Oh, you're asking. Okay, you're asking how the true sunglasses work for UV screening. They don't work this way, of course. So they're not made of materials that absorb selectively based on these considerations, light in the UV range. They're actually made of materials that, well, it depends. I mean, part of the story is also due to absorption there. But part of the story is also due to the fact that they just reduce the amount of light because you select only one polarization out of the possible, well, two components of the polarization, right? Polaroids, for example, they select just one polarization, and so you essentially reduce the intensity of the light by a factor of 2. But that will be a reduction throughout the spectrum, of course. The way the UV screens typically are constructed is in such a way that not only you get a reduction because of polarization, but you also get a reduction because of the, there is actually a filter, a material that is used filters out, I mean, based on this principle, light at frequencies higher than 3 electron volts. So there's a combination of the two. Part of the reduction is due to polarization, part of the reduction is due to particularly the one selective to UV is based on this. I actually don't know what kind of materials they use in UV, in Polaroids, in standard sunglasses, but I would suspect it's microparticles of oxides or something like that. All right.
So is it possible
Yep.
to filter just a single frequency?
Oh, is it possible to filter just a single frequency? Well, if you look at the typical band structure, you would say no. Because bands are, I mean, have a width, and there is no reason. I mean, you would really have to be to design your material very accurately in order to make sure that you only have one frequency that absorbs. If you want one frequency to be absorbed, you better stick to gases, to atoms. Atoms have typically well-defined characteristic lines of absorption, and so you want to select a single frequency, you better stick to atoms, gases, or molecules. In solids, absorptions are typically always broad because of the bands are broad.
One question.
Yep.
Okay. The example that you mentioned for those with energy curve which is greater than the visible range
Right?
are okay, like glass, something.
Yes.
They
So,
are not okay. Yeah. Okay. And when we start the lecture, we say those materials are not like they are not ordered.
oh,
Something. And then how can I mean who can?
no, I don't think there is any relationship between the order and the. So you're asking whether, I mean, you're saying that we remarked at the beginning of our classes that at least the examples I gave you for materials that are disordered, glass, polyethylene, water, because water is liquid, so it's disordered, they all happen to be transparent, belong to this category. I don't think there is any particular reason why this is so. I think it's just, I mean, by chance. There are an equally large number of materials that don't have this property and they're disordered. Simply, the most common ones happen to be. I don't think there is any connection between the two phenomena. It's just by chance.
Yeah, maybe the energy file maybe is different. So is that appropriate to argue with this?
No, I don't think there is any connection between order in the system and the presence of a gap. Not necessarily. I mean, there might be some connections, but not obvious ones, at least. Yeah. Okay. All right. I would like now, I mean, more or less I discussed optical properties in a very qualitative way. I mean, there's no time to go into any detail about that. Let me now move to transport properties. So I'm now going to discuss a little bit transport properties. Well, by transport I mean electrical transport, of course. Sorry. Electrical transport. There are several other types of transport, like heat transport, like mass transport. I'm going to concentrate on electrical transport. Electrical transport conduction is probably one of the most remarkable properties that solids have. And one of the main applications of solids is in the field of, say, they're important because they're conductive. I mean, metals and superconductors and all that. So we need to understand a little bit what determines electrical transport in solids and what are the physical phenomena that underlie electrical transport in solids. And once again, we're going to try and understand electrical transport based on our band structure picture. Because electrical transport, after all, is the transport of electrons. In a solid, of course, you have nuclei and electrons are charged particles. So in principle, electrical transport might be determined by nuclei as well as by electrons. But clearly, the nuclei are stuck in their positions. They don't move, with a few exceptions. And so the particles that are really carrying charge and carrying electrical currents are the electrons. And the electronic states of our system are completely described by our band structure. So if we want to understand electrical transport in solids, we need to start from our band structure. That will be our starting point to understand the optical properties. So let me redraw it once again, a band structure, and let me discuss electrical transport based on our band structure. Breuer zone, a band, another band, and so on and so forth. I'll be using more or less always the same qualitative plot, although of course bands can be of any kind, right? I'm just using this one because it's very simple to draw and very simple to understand. So, what do we mean by electrical transport? We mean the motion, if you wish, of an electron under the influence of an external field. So the typical experiment is that a typical situation is where you have a sample, you put it under an electric field, and you want to understand how much current is transported through the system because there is a finite electric field. Without any electric field, of course, you don't expect any current to flow. So you need electrons to be driven by an external field in order to move inside the material. So the question we want to ask now is a very simple one, and is the following. Suppose you are here, you are an electron, and you sit somewhere in your band structure. I'm not going to say yet whether this is a metal, it's an insulator, whatever. It can be anything. I'm not going to be bothered about where the Fermi level is. I'm just going to concentrate on one electron. An electron that must exist, of course, so the Fermi level must be somewhere above here. Whether it's here, and so it's a metal, or whether it's here, and so it's an insulator, it doesn't matter for the time being. I just want to concentrate my attention to one generic electron here in my system and see how this electron responds to the presence of an external perturbation. So I'm going to apply an electric field, and the electric field, of course, is going to act as a force on my electron. Okay? And it's going to do something to my electron. So what is my electron going to do? Now, before I discuss this phenomenon, I need to discuss an important property of band structures. So let me use now this corner of the blackboard to discuss an important expression, an important relationship that is going to be very useful for our purposes. What I'm going to discuss is for a given state. Okay, so this is suppose this is a given k. This the wave function here will be psi of k for this particular electron, and we know from Bloch's theorem that this is e to the I k r times u of k, where u is the periodic function. That's Bloch's theorem. What I want to calculate is what is the momentum of this state. Okay? It's an arbitrary state. It is given by this wave function, which is a solution of our periodic Hamiltonian. What can I say about the quantity p, actually p of k, which is psi k p psi k? The expectation value, actually let me use vectors. I mean, this is actually generic I can do it in 3 dimensions. So what is the momentum of this object? What can I say about the momentum of this state? I'll have to go through some mathematics now, so I hope you be able to follow me. So first thing, what can I say about I can certainly say that the E of k is equal to uk h of k, let me put vectors here to be sure, uk. So certainly the energy of this state is equal to, of course it's also equal to psi k E of k, sorry, h psi k. I hope you remember the discussions we made a few lectures ago, right? The solution of the full Hamiltonian, periodic Hamiltonian, which were given by psi k, generically by psi k, so that's their energy as a function of k. They are also solution of Hamiltonian, not really Hamiltonian, of second-order differential equation h of k, which we derived on the blackboard, for the periodic part of the Hamiltonian. So I can write the energy of my system either as in this form or in this form. It's equivalent, because we stated that finding the solution of h is equivalent to finding the solution of h of k. And I hope you remember what h of k, actually let me write it here, h of k, because I need it now. So this was delta squared plus 2i k dot delta minus k squared plus v of r. Right? H of k was this funny Hamiltonian with 2 additional terms that we derived at the blackboard some time ago. Right? We argued that you can either look for the solutions in terms of psi's, real solutions, and h, or you can look at solutions of h of k in the space of the periodic functions. And h of k is given by h plus these 2 terms. This interesting term that depends on momentum and this constant k squared here. Okay. So let me now take the gradient with respect to k of E of k. You might remember that I told you at some point that we were going to discuss this, that the velocity of a block state is given by the derivative, the slope of the band structure. That's exactly what we're going to do now. So I'm now going to take the derivative, the gradient, with respect to k of our band structure. So what is it? It is essentially the derivative of the function here in 1 dimension. Otherwise, it's the gradient in 3 dimensions. Right? So we're talking about now the gradient of the band structure at a given point. And I'm going to calculate it now. I'm going to calculate it using this expression here. So this function, E of k, depends on k in 3 places. U of k depends on k, U of k depends on k, and h of k depends on k. So there will be the gradient with respect to k of u of k, h of k, u of k, plus the gradient of h with respect to k. Remember, gradient with respect to k, right? So I have to take derivative with respect to k, not with respect to r. That's what I'm interested in. U of k plus u of k, h of k, gradient with respect to k of u of k. Right? K appears in 3 places, so I need to take a derivative in all the 3 places. And once again, let me remark that I'm talking about derivatives with respect to k. So this object here, for example, is not a momentum, because it's a derivative with respect to the parameter, not with respect to the position. This is the wave function which is periodic in the position. I'm not talking about derivatives with respect to the position. I'm talking about derivative with respect to the parameter. So you have to be careful when you think of these things. There are clearly 2 distinct variables here. One is the space variable, r, which is the real space, and k is the quantum number. And what I'm doing here is taking derivatives with respect to the quantum number, k. I need to continue on this side of the blackboard. Let me consider this term here. This is h of k, u of k. So that can be written as ek, uk by definition, right? Because u of k is an eigenfunction of h of k. Similarly, I can decide here to apply h to the left, right? And if I apply h to the left, again, u is an eigenvalue, an eigenfunction of h. So this term here can be replaced by just a number, not an operator. So let me collect first term and third term together. They both contain an e of k, right, which I can extract out because this is now a number. And then it's dk uk plus uk dk uk. And then I'm left with the second term plus uk gradient of k hk. What can I say about this term now? dk uk 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 dk uk. I can say that this is dk of uk uk, right? I just take the gradient. This is the function of 2 functions which depend on k. So I just take the gradient inside the first one first and inside the second next. But uk, if the wave functions are normalized properly, is 1 regardless of the value of k. Right? So this thing here is 1 independent of k if they are normalized properly. So the gradient of something which is always 1 is 0. So all this disappears. By the way, you'll find these kind of mathematical properties of wave functions, not specifically connected to k, but connected to other parameters, quite frequently in the future. So try to remember this, interesting property that when you derive with respect to a parameter, I mean, there are some interesting things when you derive the energy with respect to a parameter that may happen. I mean, this is not the only place in physics where deriving the energy with respect to a parameter gives rise to an interesting consequences. So I advise you to keep this in mind because it might be, you might come across it several times in the future. So anyway, for our purposes, the mathematics is clear. This is the gradient of something which is always 1, so it disappears. So we're only left with this one. So we have an important statement for the time being, that the gradient of the energy with respect to k, this derivative, is the expectation value on u of the gradient of h of k. But h of k depends on k only in two places. So it's not trivial, it's not easy, it's not difficult to carry out actually the gradient of of h of k. Let me do it. What is the gradient with respect to k of h of k? K appears here, right? So it's trivially, the first term is trivially minus h squared over 2m 2I delta, right? It depends linearly on k here. It's a scalar product. So the gradient is just the linear term. Yes?
Okay. We say actually u is not the wave function, right?
No, it's the solution of h of k.
Yeah. Okay. And we normalize psi of k, not u of k.
No, you remember when we discussed normalizations, we decided to normalize u of k, not psi of k. When we had the discussion about the normalization, we said that psi of k, we want to normalize functions within the unit cell, right? And so within the unit cell, if you take the square of the wave function, the square of the wave function of psi k is equal to the square of uk. So normalizing u or psi is exactly the same.
The other h of k is not the real Hamiltonian, and it's not in general Hermitian, but I think in this case it's Hermitian.
It is Hermitian, yes, correct, yes. You're right. So the question is whether h of k, since it's not a real Hamiltonian, whether it is Hermitian or not. The answer is yes. Yes, it is Hermitian. In fact, you can write it as a sum of real operators because it's the previous Hamiltonian plus a constant plus the momentum operator. So it is Hermitian because it's a combination of, physical operators. Yes. Okay, so gradient of k, of h of k with respect to k. First term is here. Second term is the gradient of k squared. Do you know the gradient of k squared, what it is? The gradient with respect to anything, The gradient also with respect to r of r squared.
The modulus of r squared is r dot r.
Right, exactly. So it's this must be 2r, right? Because r squared is r dot r, so you can take first the gradient with respect to the first r, and it gives you r, and then the gradient with respect to the second r, and it gives you r. Okay? So the gradient with respect to any variable, or that variable squared, is twice that variable, that vector. Okay, so I can continue here. Minus goes away, and so I have plus h squared over 2m 2k. All right. Actually, I can remove here a number of and I can collect minus h squared over m. Now you have to remind me. The momentum is P is IH, the gradient, right, with respect to R. Minus. Sorry. Now I have to be explicit. This is the gradient with respect to R, not with respect to K when I calculate the P. So here is the gradient, of course, with respect to R, right? If I don't say anything, it's the gradient with respect to R, to the position. So there's a minus, so let me put a plus here, and I have h. So then I'm left with minus h I delta, which is p, right? Am I correct? I would say so, right? Because I collect I, h, minus, and delta, and that's p. And what remains is h over m. And then here I have plus, sorry, minus now, h bar k. All right. Perfect. So what I can say is that, starting from here, gradient of with respect to k of e of k is, this was a digression on the gradient of k. I have to continue from here. It's uk h over m p minus h bar k uk. Is there a plus? Right. Thank you. Okay. So what I've shown essentially is that delta Ek is equal to this object. All right. Last step. Let me calculate this one now explicitly by replacing for psi of k u of k e to the I k r. Okay? So p of k is equal to u of k e to the minus I k dot r p e to the I k dot r u of k. Right? I'm just rewriting this by writing explicitly psi of k in terms of e to the I k r u. But when p applies to this pair of functions, the exponential and u to the right, I can do it one by one, right? So this is equal to u of k e to the minus I k dot r. Let me do it first on u. So I let e to the I k r go through, and I apply p to u, plus the opposite, right? So it's now the calculation might look a bit tedious, and it is the first time you see it. But in this calculation, the reason I like to do this calculation is that you see at least 4 or 5 interesting mathematical concepts that are quite common in solid-state physics. So that's the reason why I like to do this calculation really, extensively, because you have seen at least 3 or 4 aspects, mathematical aspects, that if you will ever have to deal with solid-state physics, you'll see it several times during your career. Okay, so I'd like to do it carefully because it's very representative of mathematical properties of blocks functions that you will certainly need to know if you become a solid-state physicist. So that's why I indulge in this kind of calculation, even though it looks a little bit boring, perhaps. All right. So the second part is p now. P applied to the plane wave. U of k e to the minus I k r. Then it's okay. P applied to a plane wave. Well, we know the outcome, right? P is minus IH gradient applied to e to the I k dot r. So delta brings me down IK, I times I minus 1 here. So this is HK e to the I k r, right? I'm sure you've done it several times. Free electrons, just the momentum of free electrons, HK. H bar k is the momentum of a free electron. So when I apply P to a plane wave, I get the momentum of that plane wave. So e to the I k dot r, H bar k, U of k. Surprise, surprise. So before we realize that that's exactly the same as what we've written here, let me comment on what we've done here. So here we have calculated the momentum of wave function psi, and we found that the momentum of a Bloch state at k can also be written in terms of the expectation value over the periodic part of the wave function of this operator, which is not the momentum, but it's momentum plus h bar plus the quantum number k. So once again, you don't need to calculate velocities or momenta using the full Bloch function, but you can do it using only the periodic part, as long as you remember to replace the momentum with this modified operator. Okay, the concept is more or less the same as the one we introduced as the one we discussed when we introduced h of k. In principle, the correct way to proceed is to calculate the eigenfunctions and everything for h. However, you may wish to do it with this special wave functions periodic part of the wave function, and then you have to modify the Hamiltonian. Same here. You want to calculate the momentum of the real wave function, you can do it this way. But if you want to use the periodic parts, you just need to modify your the operator that you use to calculate the expectation value. And that's exactly the same. So this number here is exactly the expectation value of the momentum operator for the real wave, for the full wave function. At this point, let me remark that this object is identical, well, with the exception of h bar over m, of course, constant, to the gradient of the energy. So we have an important conclusion here, which I will write in yellow to highlight it, and this is that the expectation value, well, P of k in our language, so the momentum, the value of the momentum, the expectation value of the momentum operator for Bloch state at k is equal to m over h bar gradient over k of E of k. No approximations, nothing. It's an exact statement. It's a very important statement because it gives us another good reason to like band structures. From a band structure, take just the gradient of your band energies. That's the momentum operator. That's, the value of the momentum for a Bloch state in the band structure. You don't need to calculate expectations, values, nothing. You just look at the slope here, and that will give you the value of the momentum for a particular Bloch state, particular solution of this periodic Hamiltonian. By the way, this obviously works for free electrons as well. If you have free electrons, this is k squared, right? H squared over 2m k squared. You take the gradient with respect to k, and you get k, you get h over m k, sorry, h squared over m k, m disappears, h bar, one of them disappears, and so pk is h times k. So obviously it works for plane waves, for free electrons. But it doesn't only work for free electrons, it works in general. As you remember, we discussed it a couple of lectures ago. If you're here, for example, you can say that this particular block state has zero momentum. And actually, we verified that this state has zero momentum. There was two plane waves propagating in opposite directions. Okay, so this statement is indeed general. And we can use it. It's an exact statement. There's no approximation in doing that. It took us a while to derive, but it's an interesting derivation, and it's a very strong and very powerful result in solid state theory. It's somewhat the equivalent of Bloch's theorem in terms of importance.
So,
Yes?
if we change k to minus k, then the momentum changes direction.
Sure, yes. If you change k into minus k, good observation. Because E of k is symmetric, the gradient must be antisymmetric, must change sign. So obviously P of k, an obvious consequence of this is that the P of minus k is equal to minus P of k. Yes. Correct. That's, again, an exact statement. Of course, assuming that the Hamiltonian is not time dependent, but our V is not time dependent, or there's no magnetic field, or so on and so forth. So, but anyway, generally speaking, it is true that the momentum here is exactly minus the momentum here, obviously. Right? They have opposite momentum. Everywhere in the band structure. If you're here, here, they have opposite momentum. Yes?
So it implies that even the velocities at the different points.
Yep. Yep. Yeah. What is velocity? Velocity is just momentum divided by mass, by definition. So I can introduce a V of k, if you wish. That's just pk over m by definition, right? So this is just an additional m. Wait. Yes. VKM, yeah, 1 over h bar. Sorry, 1 over h bar gradient, k. Right? 1 over h bar gradient. Yeah, the velocities are opposite. Thanks for the remark, because this is actually an interesting remark that allows me to notice that whatever the Fermi level in my system, whatever it is, for every electron that has a given velocity, there will be another electron with exactly the opposite velocity. So all the field states, if I look at all the electrons actually present in my system, which are the ones that fill the states, for every electron that I will have an electron with an opposite velocity. Right? If the Fermi level is here, all states, a state here will have another state here with opposite velocity. State here will have another state with opposite velocity. At least as far as the filled ones are concerned, which are the relevant ones, the real electrons, the electrons that exist. This is true both if I'm in a metal, but also if I am in an insulator. Because in any case, since I'm filling up to a given energy value, whatever I do, I will always have electrons with opposite velocities below that Fermi level.
So what if we have odd number of electrons, like 3, for instance?
Wait a sec. Odd number of electrons per cell, or in general?
In general, let's say we feed odd number of electrons.
Okay. Consider that when you say odd number of electrons, we say per cell. So we fill only half of it, but we have an infinite number of electrons. We have an odd infinity. Okay? So I don't think it's so relevant what you're saying, because it's...
For the one for electron which is C at k is equal to 0, does have
we are never in a situation where we have 1, 3, 5 electrons as a whole. We always have an infinite number of electrons. In some cases, they correspond to an odd number of electrons per cell. In some other cases, they have an even number of electrons per cell. But the total number of electrons is always infinity in an infinite system. So it doesn't make sense to say whether they have an odd number of electrons. Yes, okay, you may have, if the number of electrons per unit cell is odd, and you choose to go to infinity only with odd numbers of cells, okay, the number will always be odd. But we're talking about 1 electron out of an infinite number of electrons, so that doesn't really count.
Okay. Okay, here the energy is smooth, and let's say at k equal to 0, we have, and then what is the one which is with the we say for every electron we have...
Well, of course, with the exception of k equal to 0, of course, sorry, yes. With the exception of k equal to 0. K equal to 0, it's, yes.
So what does it really mean? I mean, does it have some consequence?
You're asking whether the fact that at k equals to 0 there is no opposite velocity? Well, at k equals to 0, because of k minus k, the curve must have a minimum or a maximum, must be a stationary point. And if it's a stationary point, the velocity is 0. All right? There is an exception, okay? And that's your homework. There is an exception. If you have here, the velocities of the two states are not 0, in principle. But then you have a degeneracy, and you can actually build a combination such that the two velocities are 0. I think we're talking about really sets of 0 dimensions, which is not really relevant for us.
Yeah, because something which is stationary is not physical acceptable in this.
Something that is not, sorry?
That's stationary.
No.
K equal to 0 is
No, it exists, but it's just one state out of an infinite number of states. So from a physical point of view, it doesn't really contribute to the physical properties of the system. It cannot affect, just one point affect the behavior of the whole system. One electron out of infinitely many electrons cannot really alter the behavior of the system. Okay? Okay, right. So what I wanted to say is the following, that whatever you do, with exception of sets of 0 measure, okay, let me be more precise if you wish, you always have an electron with opposite velocities. So in the stationary state, the electrons, on average, don't move. Or at least, for every electron that moves in a given direction, you have another that moves in the other direction. So there cannot be any current, net current, flowing in a system at stationary equilibrium conditions. Of course, it's obvious, right, that you don't expect any current flowing at stationary conditions, otherwise there would be something wrong. But it's interesting to see that this actually arises not just as a general principle that we impose, but actually as a result of a calculation of something that we clearly derived through our mathematics, that without any external field, the total current that flows into a system must be 0, because you have an equal number of electrons moving in opposite directions. Okay. I wonder whether I should... Yeah, sure.
Okay, we say K runs from minus pi ray to pi ray, but
yes.
We exclude one indirect.
We exclude one end. Oh, you're always talking about these sets of 0 measure. Okay. Yeah, okay. Yes, we need to exclude. Yes, if we include this one, we have to exclude the other edge. Yes. Okay. No. Of course. I mean, you're right in saying that. I mean, it's the answer to your question is that these cannot be relevant. Sets of 0 measure, one electron out of an infinite number of them cannot influence the properties, the macroscopic properties of a system. Yes. By the way, there are several other reasons why this picture is not fully valid more than what you're just arguing. I mean, think of just the number of defects that you have in a material. Can you prepare a material which is totally free of defects? No. Right? You'll always have a finite concentration of defects. What do you do with those defects? You just stay home and you don't do your theory? I mean, no. You go ahead and assume and hope that those defects are not going to affect the macroscopic properties of your system. Okay. All right. So, yeah, so that was perhaps a bit boring, but we had to go through it. And I guess we just need to remember this and, of course, the velocity here as the main result of all this mathematical derivation. Let me now introduce the electric field. What's happening when we have an electric field? Well, this electron here, regardless of where is the Fermi level, regardless of all the rest, will be subjected to a force that is given by the charge times the electric field. So it will start to do something. It was originally here, stationary, if nothing else was happening, solution of our Hamiltonian. Okay? At some point, I switch on an electric field, I perturb the system, and this electron will start to do something. It will start to go somewhere else. In fact, we're now going to use perturbation theory to try and determine what is the fate of this electron. So we're going to assume that the electron will do a sequence of transitions induced by this external perturbation between states that arise from the unperturbed Hamiltonian. So if I do that, I immediately have to assume that this is a perturbation. I have an external perturbation which induces transitions in my system, but I can still work with the basic structure of the unperturbed Hamiltonian and just study the problem in terms of jumps between eigenstates of the unperturbed Hamiltonian in order to understand the dynamics of my problem. This clearly means that I have perturbation theory in mind. If perturbation theory was not valid, namely, if this field was large enough, it wouldn't be possible for me to continue to use the unperturbed states as a good starting point to describe the dynamics. So this is to say that I'm going to use perturbation theory in some form to discuss now the dynamics of the electron in the presence of an electric field. So this state here will start evolving with time. We start having some jumping to other states in our system. Now, let's assume, and this is now an assumption, which will actually not justify, but I have to introduce it as an assumption, that the electron jumps to nearby states only in this dynamics. So it doesn't really do jumps across the gap or at long distances. Well, this assumption is justified by the fact that this is actually a static perturbation. In order to change the energy, you need to have a time-dependent perturbation. If you want to have a finite jump of energy between two states, there must be, the perturbation must have a frequency, h bar times omega, such that h bar times omega is equivalent to the difference in energy between the two states. So if you want to allow your wave function to change its energy during this process, in principle, the Hamiltonian must be time-dependent, must be oscillating, right? Only if you're allowed to jump from a final state, from an initial state to a final state, only if you have a perturbation with a given frequency. If the frequency of the perturbation is 0, like here, this is a static perturbation, in principle, you can only jump from states which are arbitrarily close to one another. Right? So I will only consider jumps between states that are arbitrarily close in energy, because that's all the other jumps are not allowed by static perturbation. So there will be, in a time delta t, the system will jump to nearby states. So it will change its k by an amount delta k, which I'm now going to determine, in a time delta t. So I suppose I take a discrete amount, time t, delta t, and I look at how much the electron has moved in our space k, how many jumps it has done, and how far it has gone from the original point. And I'm going now to determine this delta k in a given time delta t. So I'm going to look at the rate of change of my quantum number k. And how do I do that? Well, I know the amount of energy that the external perturbation is giving to my system for a unit of time, right? That's actually, so the change of energy of my particle, sorry, let me continue to use discrete time steps. The amount of energy that my external perturbation gives to my system in a time t, small t, will have to be the force acting on the electron times its velocity. Right? That's just classical mechanics, by the way. The change of energy that I give to my system has to be proportional to the force times the velocity of my particle. I put an asterisk here because this is actually true if I assume classical mechanics, which is not entirely justified because my problem is actually a quantum mechanical problem. So this is why this theory actually goes under the name of semi-classical theory. And you'll find it in books with the name of semi-classical theory of transport. All right? And the asterisk refers precisely to this approximation. Here is where I'm using classical theory. I need to warn you that all this discussion is very hand-waving and qualitative. It's certainly not as mathematically correct as the one that we carried out there. This is much more shaky, okay? But I hope you'll understand and you'll be able to capture, some of the features of this theory. So, I want to understand how much the electron is moving. So I want to understand what is the rate of change of k as a function of time. How do I determine that? Well, certainly the amount of energy that the electron receives due to the external field is, of course, F, the force is minus E, the electric field, right? Is given, at least if I assume classical mechanics, is the power, the change of energy. So it's a force times the velocity of my particle. That is. However, if my particle changes energy, changes momentum, the change of energy must be connected to the slope of the band structure. In other terms, the amount of energy that the electron, if this is the amount of energy due to the external force, the electron must be moving around this band by something which is the derivative, the gradient, let me use now one dimensions, with respect to k times dk dt. Right? That's the energy that physically I know I'm providing to the system in a unit of time. That's the energy that the electron will have to change in the band structure, and therefore, what is the rate of change in k? And if I want the two of them to be the same, these two quantities must be the same. But dE over dk is, in fact, in one dimensions, h bar times the velocity. So this is h bar times the velocity, k, dk dt. Allow me to do these considerations in one dimension, okay? So you have a single. It is also true in three dimensions, but let me do it in one dimension, so just for simplicity. Now, this is the energy that I know is pumped into the system by the external field, and this is how the energy must change if I look at it from a band structure point of view. So if there is an energy pumped into my system, the momentum must change by an amount which is given by the equality between this and this. Right? Is that clear? I mean, I'm forcing the electron to change energy because I'm pumping energy into my system by this. But the electron can only move in the band structure, right? So for a given amount of energy change, if I say the energy change must be this, that automatically defines also the amount of k that I need to move, because I can only stay in my band structure here. So if I put energy into my system, I need to change k correspondingly. And that's the rate of change in k, and that's the energy I'm pumping into my system. So I can now equate the two and find out the change of delta k in delta t, which is what I wanted. So dk over dt. V, by the way, disappears here and here, and it's just minus E A H bar. All right? So in other words, I have an external field that is forcing changes in my system. The electron will move in my band structure with a rate of change of k, which is equal to the external force divided by h bar. So if I have a constant external field, E, well, this electron will jump from one state to another one at a constant rate. So it will just move with a constant velocity, not real velocity, right? Velocity in the space of the k, in this quantum number. Will change k with a rate which is uniform, which is constant, if the external field is constant. So an electron originally here, I switch on the electric field, we start just moving with a constant speed in k space in my band structure. Of course, when it reaches this point, there is periodic boundary condition, so it will re-enter from here. So it will just continue. Tum, 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 tum. Yeah.
How do I mean? The result looks a bit weird. I don't know. Maybe
It is weird, yes.
yeah. How? I mean, we have now we have neighbors. I mean, neighbor electron, for instance.
Yes. You mean two electrons here?
For instance, yeah, and then
Oh, they move together. They move like pairs, so they never hit.
the whole thing moved.
Of course, because this is true for every electron, right? There's no distinction whether it's here, 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 here. And the nice thing is that they actually move with the same speed. So they never clash. So it's like a worm. It's like a train that moves
So they have
a
one
constant,
mode, like one mode.
a single velocity. Yes, all of this doesn't depend on k here. You see, this is just a constant. It doesn't depend on k.
Okay, is it always true for okay, I mean for which time scale if the time scale is large?
Oh, yeah. That's we've made some approximations, right? But it's not that far from being the truth. This is actually quite true. It is like that. I know why you're worried, because how do we get from here? I mean, that's not the way I was thinking of transport, right? I was thinking of transport as a different thing. I was thinking of transport of electrons reaching a steady state of velocity or something like that, with some friction, something like that. Now we find these trains that move along the band structure and things like that. I'm afraid we'll have to stop here, and, and we'll have to continue next time if you want to know the following part of the story. We'll actually get to what you have in mind at some point, but we need to go through this before we get to that point. Actually, this is a very interesting phenomenon, this one, which has been experimentally verified, and that's the truth. You need to add more ingredients if you want to get to the point that you have in mind, namely to have a finite conductivity, electrons reaching a steady state, but we need to go through this first. Okay, so I suggest that we stop here for the time being. We are not yet over with the theory of transport. We need at least one more lecture in order to get to the final thing. So we continue on Wednesday, right? The next lecture will be on Wednesday. Test, plus we continue on this, then Friday, and then so on and so forth, okay? All right. Good. Questions? Okay.